The wind is screaming. It cuts across an empty plain of ice and broken stone, a sound so sharp it feels like it could slice skin. Snow whips sideways. The sky is the color of iron. In the distance, something moves, huge, shadowed, prehistoric. A woolly mammoth lowers its tusks and bellows into the storm. And just beyond the curtain of snow, a small band of humans, wrapped in furs, hands cracked and bleeding, tighten their grip on spears tipped with stone. This is not a myth, not a movie. This is Earth, roughly 20,000 years ago, at the height of the last ice age. And it is a world on edge. Massive ice sheets, some over 2 miles thick, smother North America, Northern Europe, and large parts of Asia. Sea levels are more than 100 meters lower than today. Entire continents are reshaped. Coastlines are unrecognizable. Where there is now ocean, there is exposed land. Where there are now cities, there is silence. Frozen, brutal silence. Temperatures plummet. In many regions, they are 6 to 8 degrees Celsius colder than modern averages. That may not sound catastrophic. It is. That small shift locks water into glaciers. It transforms forests into tundra. It drives animals and humans into constant migration. Life here is a gamble played against extinction. The Ice Age did not arrive overnight. It was the result of long-term shifts in Earth's orbit, subtle wobbles known as Milankovitch cycles that altered the distribution of sunlight across the planet. Less summer sunlight in the northern hemisphere meant snow failed to melt. Year after year it accumulated. Ice advanced. Oceans retreated. But here's the part that still unsettles scientists. The system was fragile. Climate records taken from deep Antarctic ice cores show sudden spikes and crashes in temperature, not over millennia, but sometimes within decades. In geological terms, that's a heartbeat, a blink. Imagine waking up in a world that is slightly colder than yesterday, then colder still. Rivers freeze earlier, herds migrate sooner, hunting patterns collapse. You don't have satellites, you don't have weather forecasts, you have instinct and fear. And yet, humans survive. Small, scattered populations of Homo sapiens had already spread out of Africa tens of thousands of years earlier. By the time the Ice Age reaches its peak, humans occupy parts of Europe, Asia, and possibly Australia. They paint on cave walls in Lascaux and Chauvet. They carve figurines from ivory. They bury their dead with ritual. This isn't a primitive species barely clinging to life. This is a thinking species, watching, adapting. But survival here requires something extraordinary. Picture the woolly steppe, a vast, dry grassland stretching from France to Siberia and across what is now the Bering Sea. It is one of the most productive ecosystems in Ice Age Eurasia. Herds of bison, wild horses, woolly rhinoceroses, and mammoths roam across endless horizons. Predators, dire wolves, cave lions, saber-toothed cats follow. Humans enter this arena as both hunter and hunted. They develop tailored clothing using bone needles. They construct shelters from mammoth bones and hides. They learn to read the land, the angle of snowdrifts, the migration of reindeer, the behavior of birds. Each innovation is a line between life and death. But beneath this struggle lies something bigger, something planetary. Glaciers grind across continents, reshaping mountains and carving valleys. They act like massive mirrors reflecting sunlight back into space and reinforcing the cold. Meanwhile, atmospheric carbon dioxide drops to around 180 parts per million, far below modern levels. The planet is locked in a feedback loop of ice and chill. And then, slowly, it begins to shift. Around 19,000 years ago, Earth's orbit changes just enough. Northern summers receive more sunlight. Ice begins to retreat. Glaciers melt. Sea levels creep upward. Coastlines vanish beneath rising water. But the warming is not smooth. It is chaotic, abrupt, violent. Massive pulses of meltwater pour into oceans, disrupting circulation patterns. Climate zones lurch northward. Ecosystems collapse and reform. In some regions, warming happens rapidly, temperatures rising several degrees within generations. If you are human in this moment, you feel the ground moving under your entire existence. Hunting grounds disappear, rivers reroute, new lands open, but others drown. And this is where the mystery deepens. Because when we look back at the Ice Age, we don't just see a frozen world. We see a turning point, a crucible, a test that reshaped humanity in ways we are still trying to understand. Why did some human populations thrive while others vanished? Did rapid climate swings influence migration routes? Did environmental stress drive innovation? Or did innovation allow survival in spite of stress? Ice cores, sediment layers, fossil pollen, and archaeological sites form a mosaic of clues, but the full picture remains incomplete. One thing is certain: the end of the last Ice Age was not a gentle thaw. It was a period of instability so dramatic that it forced humanity to rethink everything: movement, food, shelter, cooperation. It was the edge of extinction and the edge of transformation. As glaciers withdraw, they expose corridors of land that had been buried for thousands of years. They reshape rivers that will later nourish civilizations. They create new coastlines that early humans will follow. This frozen world, brutal and unforgiving, is not just a backdrop. It is the stage on which the next chapters of human history will unfold. 4 mysteries from this era still haunt us. They are not myths. They are scientific puzzles grounded in evidence, yet unresolved. Each one carries implications not only for our past, but also for our future. Because the Ice Age is not just about cold. It is about tipping points, sudden shifts, the fragile balance of climate and life, and the uncomfortable realization that humanity was forged not in stability, but in chaos. The ground shakes. Not from thunder, not from an earthquake, from footsteps. Thousands of pounds of muscle and fur move across the frozen plain. A woolly mammoth herd pushes through knee-high grass dusted with frost. Their breath steams in the air. Tusks curve like ivory scythes. Calves press close to their mothers. The earth feels alive. And then, silence. Because within a geological blink, they are gone. Not just mammoths, giant ground sloths the size of small cars, saber-toothed cats with fangs as long as daggers, American lions, short-faced bears taller than any grizzly alive today. In Australia, car-sized wombats and reptilian predators vanish. In the Americas alone, more than 30 genera of large mammals disappear between roughly 13,000 and 10,000 years ago. This is not a slow fade. It is a collapse. And we still don't fully know why. For over a century, scientists have wrestled with this mystery. Why did so many Ice Age giants vanish at the very moment humans were spreading across the globe? The first major hypothesis is brutally simple: overkill. In the 1960s, ecologist Paul Martin proposed what became known as the Blitzkrieg model. The idea is stark. Modern humans armed with advanced stone tools and cooperative hunting strategies entered new continents and hunted large animals faster than they could reproduce. The timing is suspicious. Humans arrive in North America around 15,000 years ago, possibly earlier. Within a few thousand years, mammoths and mastodons are extinct. In Australia, humans appear around 65,000 years ago. Soon after, megafauna begin disappearing there too. Correlation is not proof, but it is hard to ignore. Archaeological sites show cut marks on mammoth bones, spear points embedded in ribs. But here's the complication. The number of confirmed kill sites is surprisingly small compared to the vast populations these animals must have had. If humans wiped them out, where is the overwhelming evidence of slaughter? And then there's climate. At the end of the Ice Age, temperatures rise dramatically. Glaciers retreat, vegetation shifts. Grasslands turn into forests in some regions, wetlands expand. In others, drought intensifies. The mammoth steppe, the vast ecosystem that sustained countless large herbivores, fragments and shrinks. Imagine being a mammoth adapted to dry, cold grasslands. Suddenly, your habitat is splintered. Food sources change, migration corridors vanish, your calves struggle to survive. Climate stress alone could push vulnerable populations toward extinction. But here's the twist. Previous ice ages had come and gone. Climate had swung wildly before. Megafauna survived those earlier shifts. Why did this time prove fatal? Some researchers propose a third factor, a cosmic one. In 2007, a controversial hypothesis emerged. Around 12,800 years ago, fragments of a comet may have exploded in Earth's atmosphere, triggering massive wildfires and abrupt climate cooling, known as the Younger Dryas. Supporters of this theory point to unusual layers of microscopic diamonds, soot, and elevated platinum levels found at certain archaeological sites. If true, the impact could have devastated ecosystems and human populations simultaneously. But the evidence remains debated. Some studies replicate the findings, others fail to confirm them. No confirmed crater of the appropriate age has been definitively linked to this event. So we are left with a layered mystery. Was it humans? Climate? Cosmic catastrophe? Or some deadly combination of all three? Let's zoom in on North America. The Clovis culture, identified by distinctive fluted spear points, appears around 13,000 years ago. For decades, it was considered the earliest human presence on the continent. Today, we know humans were there earlier, but Clovis hunters were real, skilled, mobile, highly adapted to hunting large game. At sites like Blackwater Draw in New Mexico, mammoth remains lie beside Clovis points. The image is powerful. Human ingenuity meeting prehistoric power. But mammoths had survived hundreds of thousands of years of predators before. Wolves hunted them, lions hunted them. Why were humans different? Because humans don't just hunt. We strategize. We track migrations across seasons. We coordinate. We use fire. We share information. A small band of determined hunters targeting breeding females could destabilize entire populations over generations. Now, layer climate stress on top of that. Populations already weakened by habitat fragmentation become more vulnerable to even modest hunting pressure. A tipping point emerges. And tipping points are unforgiving. In South America, giant ground sloths and glyptodonts disappear. In Eurasia, woolly rhinoceroses vanish. Even on islands thousands of years later, like Wrangel Island in the Arctic, isolated mammoth populations persist until around 4,000 years ago before finally dying out, likely due to genetic decline and environmental stress. The pattern suggests something complex, not a single cause, but an intersection. A world already destabilized by climate change meets a new, highly efficient predator. Us. And this is where the story becomes uncomfortable. Because if human arrival consistently correlates with extinction across continents, Australia, the Americas, Madagascar, then the Ice Age extinctions may represent the first global ecological footprint of our species. Not agriculture, not industry, but stone-tipped spears and organized cooperation. Yet, there's caution here. Recent studies using improved carbon dating suggest some megafauna populations were declining before clear evidence of widespread human hunting appears. In some regions, extinctions do not perfectly align with human arrival. In others, they do. The data resists simplicity. which is exactly why this mystery still matters. Because understanding what happened to the mammoths is not just about the past, it's about resilience, about how ecosystems respond to rapid change, about how new pressures, whether climatic or human, can cascade through food webs. Stand again on that frozen plain. Hear the wind. See the mammoth herd moving across a landscape that has sustained it for thousands of years. And then imagine that within a handful of human lifetimes, it disappears forever. No bones bleaching slowly into myth, no gradual fading, just gone. Something fundamental shifted at the end of the Ice Age. Whether by spear, by storm, or by skyfire, the giants fell, and with them, entire ecosystems reorganized. Forests expanded where grasslands once dominated, predator hierarchies changed, human diets diversified, mobility patterns adjusted. The world that emerges after the megafauna collapse is not the world that came before. And that shift, sudden, irreversible, marks one of the first great ecological turning points shaped, at least in part, by our own species. The giants vanished, but the question they leave behind is still walking beside us. What truly killed the mammoths? The cold comes back without warning. One generation is watching glaciers retreat, rivers swell with meltwater, grass pushes through soil that has been frozen for 20,000 years. The air softens, herds expand northward. For a moment, just a moment, it feels like the worst is over. And then the sky changes. Temperatures plunge, not gradually, not politely. They crash. Around 12,900 years ago, in what should have been a steady warming trend toward the modern climate, Earth snaps back into near-glacial conditions. In Greenland ice cores, the signal is unmistakable. Temperatures drop by as much as 10 degrees Celsius in a matter of decades. Decades, within a single human lifetime. This period is called the Younger Dryas, and it is one of the most abrupt climate reversals ever recorded. Imagine you are alive at this moment. Your parents remember advancing warmth, new forests, shifting animals. You expect expansion, opportunity. Instead, winters intensify, growing seasons shorten, storm tracks shift, entire ecosystems lurch backward into cold. It is not just colder, it is unstable. Ice core records from Greenland, particularly the GISP2 and GRIP cores, preserve tiny bubbles of ancient atmosphere. These bubbles tell us carbon dioxide levels remain relatively steady, but temperature plummets. Oxygen isotope ratios shift sharply. Dust concentrations spike, suggesting stronger winds and drier conditions. Something massive has disrupted the system. The leading explanation centers on ocean circulation. During the warming phase that preceded the Younger Dryas, enormous glacial lakes formed along the margins of retreating ice sheets in North America. One of the largest, Lake Agassiz, held more freshwater than all of today's Great Lakes combined. At some point, that freshwater may have surged catastrophically into the North Atlantic. Why does that matter? Because the Atlantic meridional overturning circulation, the Great Ocean Conveyor Belt, depends on salty, dense water sinking near Greenland to drive heat northward. If massive volumes of freshwater dilute the ocean's salinity, that sinking slows or stops. Heat transport collapses. Northern regions cool dramatically. Climate models support this possibility. Sediment cores from the North Atlantic show changes consistent with disrupted circulation. Evidence of meltwater pulses appears in geological records. But here's the complication. The precise timing and routing of those freshwater floods remain debated. Some data suggest outflows occurred earlier than the onset of the Younger Dryas. Other studies question whether freshwater volumes were sufficient to fully shut down circulation. And then there is the more explosive hypothesis: a cosmic impact. In 2007, researchers proposed that fragments of a disintegrating comet exploded over North America around 12,800 years ago. According to this theory, the airbursts ignited continent-wide wildfires, injected massive amounts of dust into the atmosphere, and triggered abrupt cooling. Supporters cite a thin, dark sediment layer, often called the black mat, found at numerous archaeological sites across North America. Within this layer, they report elevated levels of platinum, magnetic spherules, and nanodiamonds, materials that can be associated with high-temperature cosmic events. If true, it would mean the Younger Dryas was not merely a climatic hiccup, but a planetary shockwave from space. But the scientific community remains divided. Multiple independent teams have failed to replicate the impact markers. No confirmed crater of the appropriate age and scale has been definitively linked to the event. Some supposed nanodiamonds have been reinterpreted as terrestrial materials. The evidence is intriguing, but inconclusive. So we stand between two powerful possibilities: ocean disruption from glacial meltwater or an extraterrestrial trigger. Perhaps even both. What makes the Younger Dryas so unsettling is not just its cause, it is its speed. Climate does not gently glide into new states, it flips. For roughly 1,200 years, cold conditions dominate much of the northern hemisphere. Glaciers stabilize, vegetation retreats southward. Human communities that had begun adapting to warmer conditions are forced, again, to improvise. In the Levant, in the region that will one day become the cradle of agriculture, the Natufian culture experiences this shock directly. Archaeological evidence suggests these semi-sedentary hunter-gatherers had begun relying heavily on wild cereals during the warming period. Then the Younger Dryas strikes. Colder, drier conditions reduce the availability of wild grains. Settlement patterns shift. Some communities disperse, others intensify resource management. And here is where the mystery deepens into consequence. Some researchers argue that the environmental stress of the Younger Dryas may have accelerated the transition towards deliberate cultivation. Faced with unpredictable wild harvests, humans begin experimenting with controlling plant growth. If that's true, then a sudden climate reversal born of ocean chaos or cosmic fire may have nudged humanity towards agriculture. Think about that. A planetary cold snap potentially forcing the earliest seeds of farming. But even beyond human history, the Younger Dryas demonstrates something profound about Earth's climate system. It has thresholds. Push it far enough, and it responds not linearly, but dramatically. Greenland ice cores show that when the Younger Dryas ends around 11,700 years ago, warming resumes just as abruptly as the cooling began. Within decades, temperatures surge upward again. The Holocene, the relatively stable climatic period in which all recorded civilization develops, stable, but only after chaos. The Younger Dryas is not just an academic puzzle, it is a warning etched into ice. The climate system can reorganize itself with shocking speed. Feedback loops, ocean currents, atmospheric dust, ice reflectivity can amplify disturbances beyond what seems possible. We often imagine ancient climate as slow and predictable. The Younger Dryas shatters that illusion. Picture a campfire on a cold night 12,000 years ago. A group of humans sits close, listening to the wind. They do not know about ocean currents or isotopes. They only know that winters have grown harsher, that animals migrate differently, that familiar patterns are breaking. To them, it feels like the world is unstable. And in a sense, it is. Because the Younger Dryas represents one of the clearest examples in Earth's recent history of abrupt climate change, rapid enough to transform ecosystems, migrations, and possibly the trajectory of human innovation. The cause remains debated, the trigger uncertain, but the impact is undeniable. The Ice Age does not end smoothly, it convulses. And in that convulsion, humanity is tested again, forced to adapt not to slow transformation, but to sudden reversal. A warming world snaps back to ice, then snaps forward again. The question that lingers is not just what caused it, it is whether such tipping points are still possible. The ocean is gone. Not forever, not yet, but 12,000 years ago, where waves now crash between Siberia and Alaska, there is wind instead. Endless wind sweeping across a vast exposed plain of grass, sedge, and scattered shrubs. Herds move across it, caribou, steppe bison, perhaps even mammoths in earlier millennia. And somewhere on that open land, humans are walking. This is Beringia, the land bridge that once connected Asia and North America. At the height of the Ice Age, global sea levels were more than 100 meters lower than today. So much water was locked in ice sheets that entire continental shelves rose above the surface. Beringia was not a narrow strip. It was a subcontinent over 1,000 kilometers wide in places, stretching from modern-day Siberia into Alaska. For decades, this land bridge has stood at the center of one of the most profound questions in human history. How and when did the first people enter the Americas? The traditional model, taught for much of the 20th century, seemed clean and logical. Around 13,000 years ago, as ice sheets in North America began to retreat, an ice-free corridor opened between the Laurentide and Cordilleran ice sheets. Through this corridor, groups associated with the Clovis culture moved south, spreading rapidly across the continent. It was neat, chronological, elegant, and it is now incomplete. Because archaeological discoveries over the last few decades have complicated the timeline. Sites such as Monte Verde in Chile suggest human presence in South America as early as 14,500 years ago, perhaps earlier. That means humans must have entered North America before the ice-free corridor was fully viable. So how did they do it? One hypothesis proposes a coastal route. Imagine small groups moving along the Pacific shoreline using simple watercraft, harvesting marine resources, hugging the edge of ice sheets. The coastline would have offered kelp forests rich in fish, shellfish, and sea mammals, a kelp highway stretching from Asia down into the Americas. The problem? Much of that ancient coastline is now underwater. When sea levels rose rapidly after the Ice Age, they drowned early settlement sites beneath tens of meters of ocean. The archaeological record is literally submerged. But genetic evidence adds another layer. Studies of mitochondrial DNA suggest that the ancestors of Native Americans diverged from East Asian populations roughly 20,000 to 25,000 years ago. That's earlier than the classic Clovis timeline. Some researchers propose a Beringian standstill model, suggesting that human populations may have lived in Beringia itself for thousands of years, isolated by surrounding ice sheets before eventually dispersing into the Americas. Picture that, a population stranded, not in desperation, but in adaptation, on a wind-swept plain between continents, living there for millennia, developing distinct genetic signatures, waiting, perhaps unknowingly, for glaciers to shift and open new corridors southward. But Beringia itself remains mysterious, because much of it is now beneath the Bering Sea. Sediment cores pulled from the seafloor reveal pollen from grasses and shrubs, confirming that it was not a barren wasteland, but a habitable environment. Animal remains show it supported diverse megafauna. It was not merely a bridge, it was a homeland. Yet direct archaeological evidence from central Beringia is scarce because the land is submerged. So we are left reconstructing migration routes from fragments. Stone tools in Alaska, genetic patterns in modern populations, radiocarbon dates from cave sites in Yukon and British Columbia. Each clue pushes the timeline slightly earlier, slightly more complex. And complexity is the key. The story is no longer a single wave of migration through a single corridor. It may have been multiple waves, some perhaps moving inland when corridors opened, others hugging coasts. Some populations may have vanished entirely, leaving faint genetic traces. Others expanded and diversified across two vast continents. Now consider the scale of what they faced. Ice sheets towering kilometers high blocked vast regions of North America. Glacial lakes the size of small seas formed and drained unpredictably. River systems were unstable. Climate oscillated violently, especially during events like the Younger Dryas. These were not gentle migrations. They were high-risk expansions into unknown territory. And yet, within a few thousand years, humans had reached the south tip of South America, from the Arctic to Patagonia. That speed suggests extraordinary adaptability, but it also raises a deeper question. What knowledge did they carry with them? Because migration is not just movement, it is information transfer. Hunting strategies, tool-making techniques, social structures, navigation skills. The people who crossed Beringia were not wandering blindly. They were tracking herds, reading landscapes, observing seasonal shifts. They were decision-makers under extreme uncertainty. And here is where the mystery tightens. If humans were in the Americas earlier than once believed, perhaps as early as 16,000 or even 20,000 years ago, then the Ice Age landscape they encountered was different from the one Clovis hunters later knew. Glaciers were more extensive, coastal lines narrower, ecosystems distinct. That means our understanding of early American settlement is still evolving. Every new site discovered forces a recalibration. The land bridge that once seemed like a simple highway now appears as a dynamic, shifting environment, sometimes passable, sometimes isolated, sometimes submerged. And the rising seas erased much of the physical evidence. Stand now on the coast of Alaska. Look out over the gray water. Beneath those waves lie plains where people once walked, campsites, fire pits, tools lost in soil that is now ocean floor. An entire chapter of human migration drowned by post-Ice Age sea level rise. The Ice Age did not just reshape continents, it erased evidence, which means the story of how humans entered the Americas remains partially hidden, locked beneath sediment and salt water. But what we do know is this: Beringia was not merely a crossing, it was a filter, a testing ground, a climatic bottleneck that shaped the genetic and cultural foundations of entire civilizations to come. The path into the Americas was carved by ice, exposed by falling seas, and later erased by rising waters. And the mystery of that journey, its timing, its roots, its pauses, continues to evolve with every new fragment of bone, every submerged core sample, every recalibrated date. Because somewhere between Siberia and Alaska, between ice sheets and open ocean, humanity stepped into a new world and changed it forever. The fire is small. It flickers against a wall of stone, throwing shadows that dance like spirits. Outside, the wind moves across a landscape still scarred by ice. The great glaciers are retreating now. Rivers swell with meltwater. Forests creep north. The air feels different, less brutal, but uncertain. A group of humans sits close together, not wandering tonight, not chasing herds, staying. And that decision to stay may be the most revolutionary act of the Ice Age. because when the Younger Dryas finally releases its grip around 11,700 years ago, the world enters a new climatic chapter, the Holocene. Temperatures stabilize, rainfall patterns settle into something resembling predictability. Seasons become more reliable. For the first time in tens of thousands of years, the climate stops convulsing. And in that stability, something ignites. But here's the mystery. Did humans invent agriculture because the climate became stable? Or did they invent it because instability forced them to experiment long before stability arrived? Let's go back to the Levant, modern-day Israel, Jordan, Syria, at the edge of the Ice Age. Before full agriculture, there were the Natufians, semi-sedentary hunter-gatherers who built stone structures, stored food, and relied heavily on wild cereals. Archaeological sites like Ain Malaha show evidence of long-term occupation, circular houses, grinding stones, burials beneath floors. They were not yet farmers, but they were no longer purely nomadic. Then the Younger Dryas strikes. Cooler, drier conditions reduce the abundance of wild wheat and barley. Gazelle populations fluctuate. Environmental predictability shatters. And here's where tension becomes transformation. Some communities disperse, returning to more mobile lifestyles. Others double down. They intensify harvesting. They begin managing stands of wild grain more deliberately. Over generations, subtle genetic changes appear in plant remains, non-shattering seed heads, a key marker of domestication. It doesn't happen overnight. It happens slowly, experimentally, under pressure. Was this innovation born of opportunity or desperation? Climate data suggests that as the Holocene begins, rainfall increases in parts of the Near East. Wild cereals flourish again. But now, humans have knowledge. They understand planting cycles. They recognize which seeds perform better. Within a few thousand years, full-scale agriculture emerges. Wheat, barley, lentils, goats, sheep. Permanent villages grow larger. Storage pits multiply, social structures become more complex, trade networks expand. And from this pivot, this shift from mobility to settlement, all known civilizations will eventually rise. Cities, writing, states, empires, all trace their roots to this post-Ice Age transformation. But agriculture did not emerge everywhere at once. In China, rice cultivation develops independently. In Mesoamerica, maize domestication unfolds thousands of years later. In New Guinea, root crops are managed early. Each region responds differently to climate shifts and ecological opportunity. Which raises another question. Was the Ice Age a global forcing mechanism that nudged multiple populations toward innovation? Or were these transitions inevitable once Homo sapiens reached a certain cognitive and social threshold? Let's widen the lens. The end of the Ice Age also reshapes coastlines dramatically. As glaciers melt, sea levels rise more than 100 meters over several thousand years. Vast coastal plains, once inhabited, are submerged. Some of the richest early human environments disappear beneath water. Doggerland, which once connected Britain to mainland Europe, sinks beneath the North Sea. Sundaland, linking Southeast Asian islands, fractures as oceans flood lowlands. Coastal migration routes vanish. Entire communities may have been displaced by rising seas. Did those pressures accelerate technological innovation? Did forced relocations increase contact between groups, spreading ideas faster? We cannot see most of those drowned settlements, but we can infer their existence from submerged forests, sediment cores, and scattered artifacts. The Ice Age did not simply end, It rearranged the chessboard of human geography. And within that rearrangement lies the final mystery. Why did Homo sapiens survive and thrive while other human species did not? Neanderthals vanish roughly 40,000 years ago. Denisovans fade into genetic traces. Yet modern humans expand relentlessly across every continent except Antarctica. Adaptability is the obvious answer. But adaptability to what? Extreme cold, rapid warming, megafaunal collapse, abrupt climate reversals, rising seas, shrinking habitats. The Ice Age was not a single event, it was a series of shocks, and humanity endured them all. Perhaps it was social networks, larger, more interconnected than those of other hominins. Perhaps symbolic thinking, allowing flexible problem solving. Perhaps sheer demographic momentum. Or perhaps it was timing. Homo sapiens arrived on the global stage just as climate volatility intensified. We were forged in instability, conditioned by unpredictability, trained through necessity to innovate quickly. By the time the Holocene offered stability, we were ready to exploit it. The Ice Age, in this sense, was not merely a frozen backdrop. It was a crucible. It tested human limits. It erased giants. It drowned landscapes. It froze and thawed the planet in violent pulses. And out of that chaos emerged agriculture, permanent settlement, and eventually civilization itself. But here is the quiet truth that lingers beneath all four mysteries. The climate that allowed civilization to flourish, the stable Holocene, has lasted only 11,700 years, a blink in geological time. Before it, abrupt shifts defined the planet. The mammoths fell. The younger Dryas snapped the world back to ice. Land bridges rose and sank. Humans were pushed, tested, displaced. We survived. We adapted. We transformed the planet in return. But the Ice Age leaves us with a final, uneasy question. If Earth's climate once shifted so suddenly, if tipping points once flipped within decades, could they shift again? The frozen world that shaped humanity is not ancient mythology. It is recorded in ice cores, sediment layers, genetic sequences. It reminds us that stability is fragile, and that the forces that changed humanity forever are still part of the same Earth system we inhabit today. The fire in that stone shelter burns low. Outside, the ice retreats. Inside, someone scatters seeds deliberately into soil for the first time. A small act, a quiet act, one that will echo through every city, every nation, every civilization to come. Born from ice, forged by mystery, changed forever.